Hello dear students, hopefully you are safe and healthy with your families. I have prepared this video to help Senior 6 chemistry students understand Unit 7, which is about solvent extraction and colligative properties. We are going to focus on the partition law and solvent extraction in this session. The learning objectives we have are to be able to explain the partition law as applied to separation of mixtures, specifically solvent extraction. Number 2, we have to determine the amount of solute that can be extracted in the solvent by calculations. You are going to enjoy the session, I believe so. Let's begin with explaining what is partition law. Partition law, also known as distribution law, applies to a situation where a solute X that is soluble in both two immiscible solvents. The example that we have here shows it that iodine is soluble both in water and in ether, but iodine is more soluble in ether than in water. In this case, we have iodine that is partly dissolved in water and in ether. So the word partition means that the substance is partly distributed between two phases in a dynamic equilibrium. The two phases, the one that is purple and another one that is yellow, are in equilibrium, and then a part of iodine dissolves in water, another part of iodine dissolves in ether. This kind of equilibrium that has been established is heterogeneous equilibrium because the phases that we have are separate and they have distinct separations or boundaries. It was first given by Nest while studying the distribution of several solutes between different appropriate pairs of solvents. Walther Hermann Nest was a German chemist known for his work in thermodynamics, physical chemistry, electrochemistry, and solid-state physics. Nest won a Nobel Prize in chemistry in 1920. Let's use this diagram to make clear what is partition law. While studying about partition law, Nest considers two immiscible solvents with one solute that can dissolve in both solvents. And we have a part dissolved in one solvent and another part that is dissolved in another solvent. So, initially, the solute is dissolved in one solvent, and then another solvent is added later on. Then the particles of the solute start moving from the first solvent, like water here, going into the second solvent, which is S in this case. And this happens until a dynamic equilibrium is established between the solute X that is dissolved in water and the solute X that is dissolved in the solvent S. From this observation, the following law was elaborated. It was found out that at constant temperature, the ratio of equilibrium concentrations of a solute distributed in two immiscible solvents was always a constant. which means that if the temperature is maintained constant, actually the concentrations of the solute in both solvents gives a constant value. Mathematically, we have Kd, that is known as partition coefficient, that is equal to the concentration of the solute to the in one solvent to the concentration of the solute in another solvent, and these were measured at equilibrium. So the law of partition has applications. One of the applications it has is in solvent extraction. But what is solvent extraction? Solvent extraction is the removal of a solute from an aqueous solution by an organic solvent. It is the most important application of the partition law because it helps the separation of a solute from a given solvent using another solvent that can dissolve better the solute than the first solvent. Here we have an example. Iodine that is initially dissolved in water, that is initially mixed with water, can be separated from water by using another solvent. In this example, hexane, which is an organic solvent, because hexane is an organic solvent and it dissolves better iodine, which is a non-polar covalent molecule. The image here shows a chemist who is extracting a certain solute using another solvent. Let's see step by step what is solvent extraction or how it can be carried out. So as I have said before, initially the solute is mixed with one solvent. In most cases it is water. That's what we have here, iodine that is in water. Then another solvent, in most cases an organic solvent, is added to the mixture, that is a mixture of water and the solute, with the intention of separating the solute from water. In this example, we have water that was containing iodine, then an ether is added to separate iodine from water. The distribution ratio is more in favor of organic solvent, which drives most of the solute, like iodine here, into organic solvent. So people actually ask themselves, why is the distribution ratio more in favor of the organic solvent? It's because the solute that is dissolved in water is a covalent compound, and covalent compounds are more soluble in organic solvents than in water. In that case, when the solvent is added to aqueous layer, the solute first moves from water going into the organic solvent. And when this is allowed to stand for some time, a certain dynamic equilibrium is established, and we have two distinct layers or two separate phases. One phase or one layer is the layer of the water containing the remaining part of the solute, and another layer is the solvent that is added with the solute that has already moved in it. Again, I emphasize on the fact that we call the law partition law or distribution law to mean that the solute is partly dissolved in both solvents, or the solute is distributed in both solvents. What is done next? Since most of the solute has moved into organic solvent layer, the lower aqueous layer is run out of the funnel, leaving the organic layer behind. This is what is done. It means that the tap is open and then they run out the aqueous layer, and then the solvent and the solute remain mixed in the funnel. So this mixture of iodine and ether is then transferred to a distillation flask to separate the solute from the organic solvent. Here I want to challenge you with a question. Suppose that by mistake you pour table salt into oil, cooking oil, and then you are asked to separate the cooking oil from, to separate the salt from the cooking oil. So try to make a connection between what I have already explained with that situation and suggest a way you can separate the table salt from the cooking oil. So here we have an example that we can use to quantitatively determine the amount of the solute that can be extracted by a given solvent from aqueous layer. The example we have here is that of ammonia that was containing or that was contained in water, and then you are asked to separate it from water using ethoxyethane, which is an organic solvent. So here the amounts are given. 0.1 mole of ammonia that was in 100 centimeter cubed of water were shaken with 50 centimeter cubed of ethoxyethane, and the mixture was allowed to settle. They came to a dynamic equilibrium. If the distribution coefficient, that's Kd, of ammonia in water and ethoxyethane is 8.0, you are asked now to calculate the amount of ammonia extracted into ethoxyethane. After calculating it, you are also asked to determine the percentage of ammonia that remained in water. As we have said that it's partly removed, it's not completely removed if it is done once. So to solve this problem, we use what we call ICE table. ICE stands for initial changes equilibrium. In the table, we complete by filling in ammonia that is in aqueous layer and ammonia that is in ether, and these are in equilibrium. At initial time, at the start, we had 0.1 mole of ammonia in the aqueous layer. How much was there in the ether? At initial time, there was 0 ammonia molecules because ammonia molecules were not yet moved to ether solvent. When these are shaken together and it is allowed to reach equilibrium, some changes occur. what are the changes? The amount of ammonia that was in the water starts decreasing by X amount, to mean that the amount is not yet determined. We call it X, and we put negative to mean that the amount of ammonia in water starts decreasing with time, because ammonia, which is a covalent compound, will run to dissolve in ether, which is an organic solvent, and then the amount that has run into ether is X, because the same amount moves from water and goes to ether layer. At equilibrium, we have the amount of ammonia that is remaining, and this is equal to 0.1 minus X that has gone into ether, and then we have the remaining amount. Then what is the amount extracted or that is dissolved in ether at equilibrium? It is equal to zero amount we had at initial time plus X amount that has moved into ether. Now we have X mole. So to calculate the amount extracted into ethoxyethane, as it is asked in part A of this question, we use partition law. Partition law says that the ratio of the equilibrium concentration of the solute in both immiscible solvents is always a constant. That's what we have here. Since we have all the values, now let's substitute the numerical values in the relation we have here. So you can see that Kd, which is partition coefficient, is equal to 8, and then the molar concentration of ammonia in the ether is equal to the number of moles of ammonia into the volume, by the volume of ethoxyethane, that is 50 centimeters cubed, then over the concentration of ammonia in water, that is equal to number of moles of ammonia at equilibrium in water, that is 0.1 minus X, divided by 100, that is the volume of water layer. This is in mole per centimeters cubed. We have not changed the volume into decimeters cubed because actually here we are going to cancel the units. There is no need. Then after solving for X, we find that the amount of ammonia extracted is equal to 0.08 moles. In part B, they have asked us to calculate the percentage of ammonia remaining in water. The percentage of ammonia remaining in water is obtained first of all by calculating the amount of ammonia that remained in water, that is equal to 0.10 minus 0.08 that has been extracted, divided by the total amount, that is 0.1, then times 100%. In that case, we get the percentage of ammonia that remained in water. Here you can see that what remained in water is less, again to emphasize on the fact that the solute is more soluble in organic solvent than in water. So here it's clear that 80% of the solute has been extracted by the solvent, and 20% remained in the aqueous layer. So this is an example that we have done together. So you will be given more other practice exercises so that you can get familiar with these calculations and you can actually handle different situations that is related to quantitative aspect of this partition law and extraction of the solvent, the extraction of the solute. Thank you very much. I think you have enjoyed the session.